welcome to day 11 of teaching myself linear algebra just using ChatGPT. Bunch of prompts. They developed me a curriculum. It's supposed to take about 3 weeks, so I'm right at the halfway point today. And I actually only have about 30 minutes today. It's supposed to be an hour per day. I'm going to have today be my cheat day, try to whiz through it in 30 minutes. If I have 30 minutes later, I may do a second live stream. We'll see though. Adult life gets busy. But without further ado, let's jump into this stuff. So I'm reviewing last time. Here's a 2D null space. It asked me to solve x equals 0, write the general solution in parametric form, find a basis for the null space, take the dimension of the null space. You know what? I should do this to start. This is a good warm-up, I presume. Although today's lesson, I think, is actually some new material on doing transformations of matrices and 3D space. It seemed like it was important. So I may have to hop in for a second 30 minutes later today. But that's all right. Let's go and do this. So ax equals 0. The way I set this up, I have a equals 1, 2, 3, 4, 0, 1, 2, 3. This is still on my day 10 linear algebra notes. I guess I should start new notes after I finish this. And I want a general solution in parametric form. Well, I think that the x vector has to be something like x1. I think there's 4 variables because there are 4 columns in this. So that's the x vector, x1, x2, x3, x4. I need to multiply these to get the 0 vector. So the way that I set that up, I believe, is I go x1 plus x2 plus x3 plus x4. Oh, whoops, I want to put some coefficients in here. 2, 3, I'm looking at these coefficients up here, and 4. That all equals 0. And the second equation I have is going to be 0x1, so I leave that blank, x2 plus 2x3 plus 3x4. Okay. So I think to find the general solution in parametric form, yeah, I want a solution. So what I need to do here is I'd say that x2 equals negative 2 x3 minus 3 x4. I think I'll say x3 equals s, x4 equals t. So then I still need something for, well, I think I need a third free variable, but I'm not 100% sure. Express the leading variables in terms of free variables. So this first equation can then become x1 plus 2, this is okay, negative 2 x3 minus 3 x4. That's what x2 is. Plus 3, wait, instead of x3 and x4, I'm just going to say s and t. So s minus 3t plus 3s plus 4t. All right, and then that becomes this all equals 0. So x1 minus 4s minus 6t plus 3s plus 4t. So therefore I get x1 minus s, x1, equals, I'll just do it like this, s, so it's negative 2t plus 2t. And so I believe that the system is going to look like this. I think it's s, and then this is going to be 1. What is it for this? x2 is negative 2. x3 is s1, 0, plus t. Little small thing, you notice I always kind of put a hook on the bottom of my t's. I find that very helpful so you don't get them confused with pluses. Handwriting's underrated in math. So t, this is like basic pre-algebra stuff, but that's my specialty. Let's see how I am with linear algebra. I hope I'm doing this right. So t is going to have 2 for x1. That's 2t. For s2, it's -3. Yeah. For x3, it's 0. For x4, it's 1. So I think that this is the basis for the null space. All right. Nice. x3 is s, x4 is t. Just going to scroll way down. Yo, I got this right. Dimensions of the null space is 2, 1 vector per free variable. All right, that was actually kind of good. At first I felt unconfident, but then I was able to do it. Great. Going back to my curriculum, thank you, ChatGPT Deep Research. And by the way, quick note, I read every comment and I'm going to reply to them. I haven't replied to a few the last couple days. It's awesome that people are actually checking this out. I didn't think that linear algebra content would get anyone to, break away from their doom scrolling, but it is. Some people are tuning in and they've sent really nice things. My last video was a couple people sort of pointing out, bro, get a textbook. Or, I'm a college professor. You can't really learn this stuff with AI. Well, the point is, I want to push this to the limits. I'm not going to get a textbook. At the end of this, maybe I'll get a textbook or something that can give me a proper linear algebra test that's a bit more from a authoritative source, if you will, than just AI language generated. I understand how an LLM works. I know it's just putting together words and guessing that they're relevant to what I'm requesting. But I think that the point I'm trying to make is it's really good. This is like those days of Wikipedia where your teachers told you can't use Wikipedia as a source because it can't be trusted. And then you realize, oh, Wikipedia is pretty trustworthy. Although now Wikipedia has a political slant. I'm not going to get into that. But the point is, this is the early stage of technology that I think is going to be really trustworthy, is going to be very useful. And I want to push it to the limits. This is not just about my learning linear algebra. I don't really care that much if I learn linear algebra to the point of a linear algebra professor or just to a student who gets a B plus A minus in the class. That's not immensely important to me. Instead, I want you guys to see how much can you learn with AI? What are the limits of this? What are some useful tricks we come across as we're putting in prompts and trying to learn something new? So without further ado, today is linear transformations and kernels/images. Okay, we got some new terminology. I'll tell you right now, this is going to be intense. So give me this lesson. Define a linear transformation, identify the kernel. Okay, so I'm going to make some new notes here. Day 11, linear algebra. It's loading. I'm going to go and copy this. Maybe I'll also put this into Claude. I probably won't have time within this stream, but it'll be useful to cross-check it. I think that's one of the big lessons I've learned is multiple AI models are better than just one. This one has some nice context and everything, but I want to see how it goes in other models as well. Give me a challenging lesson along with some good practice problems on this linear algebra concept. One shot this prompt. All right. Going way down. So let's see how we go here. Define what a linear transformation is and connect it to matrices. Identify the kernel and image of a transformation. So we got some new terminology, kernel and image. Determine if a transformation is one-to-one or onto, okay? And understand how changing bases affects matrix representations. So a function t, where v to w is a linear transformation if it has additivity and homogeneity. All right, I need to get what those things mean. So homogeneity seems to... So the key idea is every matrix defines a linear transformation. This is insane. I'll just tell you right now, this is insane. Screenshotting all this stuff to review later. I'm getting through all the notes to review. If you look at my new tab, I have 23 of these images I still need to rate my understanding of. I basically am screenshotting everything that kind of piques my curiosity or is interesting or confusing, makes no sense. And then I review it every time I get a new tab. I built this simple Chrome extension using Cursor and AI tools to help me learn better. If you want it, DM me on Twitter or X, and I'm happy to share the extension with you guys. It's not like it's some super classified intellectual property right now. It's just a useful little tool for learning math, what I found. So a linear transformation has additivity and homogeneity. I'm going to write that. Linear transformation so we have additivity, meaning you can add vectors within it, and I guess you can multiply by, do scalar multiplication within it. And homogeneity. You can just dash these because these are key terms I need to learn. The key idea is that every matrix with an m by n set of real numbers defines a linear transformation. This maps inputs from Rn, the domain, to outputs in Rm, the codomain. So I'm going to write those down here too. Rn equals domain. Rm equals codomain. And then these are both for an m by n matrix, right? For R is m by n. So that's rows by columns. So the number of rows, the outputs in the rows is the codomain. So I basically, one of the key things that has not yet fully clicked for me in linear algebra is why matrices? What is a matrix? Why is that a useful and sort of fundamental way of displaying information? I'm actually going to ask that right now. Why matrices? Why are these a fundamental way of containing information? They seem kind of arbitrary to me. So help me understand what their rows and columns mean and why they mean that, and why they are important to mathematics / the universe as a whole. Let's see what it says to this big prompt. And this seems like something I should put in another chat too, because it doesn't need context necessarily for this. This one I'll put into Gemini. Why not? I don't want 2.0 Flash. Give me that 2.5 Pro. All right. Oof, it had a network error occur. Whoops. So anyways, linear transformations. A matrix is a machine. Input a vector, output another vector. Yo, they literally answered my question kind of right there. A matrix is a machine. Input a vector, output a vector. Let's see if I capture that full screenshot here. Yeah, matrix is a machine. Input a vector, output another vector. So it's a function for vectors, basically. So kernel and image. The kernel of T, it's the null space of the matrix A. I don't know what T is. Subspace of the domain. It tells us what gets flattened onto 0. So the kernel of T, we have an x vector that is an element of V, such that T, when you put the vector into this matrix, you get the 0 vector. This reminds me of the A x vector equals B vector format. And then the image, also called the range or column space, okay, is everything that T can output. All right, It's a subspace of the codomain. Man, this stuff is tricky. All right, one-to-one and onto. A transformation is one-to-one if there's no collapse, no free variables, full column rank. And it's on, and this is injective. So I'm screenshotting literally everything here because it seems really information dense and important. And write these things down. So one-to-one. I vaguely know this from algebra, which is injective and onto, which is surjective. This is going to take a while to click, I know that. A transformation is onto if the image of T equals W equals the column space equals the codomain. It must have a pivot in every row. Every vector in m-dimensional space is reachable. It's onto if vectors don't get squashed together. There's no collapse, no free variables, full column rank. No free variables, one-to-one. And pivot in every row is onto. All right, let's look at this guided example. So let A equal this, 1, 2, 3, 0, 1, 4. Define T of x equals A, x vector, as a transformation of three-dimensional space to two-dimensional space. You find the kernel of T. I already solved this in a previous lesson, apparently, but it's the span of this, which is the dimension of this is 2, so it's not injective. It's not one-to-one because one-to-one would always have a kernel that is 0. And a kernel is the null space. So there's no null space, but there is a null space for this because it's a two-dimensional null space. Yeah, okay. Image is the column space of A, has 2 pivot columns. These are both pivot columns, 1, 0. Yep. Image is a 2D subspace of R2. It must be all of R2. Okay. Finish generating the lesson above. All right, there's a lot of crazy stuff here with matrices. I'm going to read through this. Why matrices? A matrix tells you what space you're working in, what directions exist there, how those directions interact and transform, how input transformation gets turned into output. It's not just a grid of numbers, it's a map, a machine, and a lens. This makes matrices the universal interface between geometry, algebra, data, movement, symmetry, and logic. Whoa. This is big time. Screenshotting that. What do the rows and columns of a matrix actually mean? Let's say that A is an element of an m by n set of numbers. The columns are as the matrix is acting on this many inputs. That's the input space. The rows is outputting vectors in this. This is the codomain. Each column shows what the matrix does to a base vector in the domain. Okay, a basis vector in the domain. And then each row encodes a linear constraint on the input vector, like an equation in a system. So I kind of get that rows are like equations and columns are like the basis vector, like, you know, saying what each variable is. I see them as systems of equations, kind of. Someone said that to me in a comment, and I guess that is sort of the simplification of all this. All right, let's say the matrix flips vectors across the x-axis. Why? Column 1, 0, this is what happens to this vector. It goes 0, 1, this is what happens to this vector. That's the full definition of the transformation. What does it do to the basis vectors? And since every vector is built from the basis, you now know what the vector does to everything. The columns encode the transformation. That's crazy. I don't really get that. I'm going to ask for more explanation here. Why are matrices important to the universe? Because the universe is structured, and matrices are how we represent and manipulate structure in virtually every field. Matrices rotate, reflect, scale, and shear space. I know what shearing space is. Every symmetry of a geometric object can be written as a matrix. Matrices preserve structure, linearity, which is the simplest form of change. Linearity is this. There's a lot here. I'm screenshotting so much of this because it's conceptually rich. Matrices describe coordinate transformations, like going from Earth to a spaceship. Yeah, okay, that makes sense. Coordinate transformations make sense. X, Y, Z. Quantum mechanics, observables like momentum and energy are matrices, they're operators. Maxwell's equation and relativity expressed via linear systems, matrices. Cool. I didn't know all this, but this is interesting. In data science and machine learning, a data set is a matrix. Rows are examples, columns are features. A neural network is just a sequence of matrix multiplication and non-linearities. PCA, SVD, dimensionality reduction, matrix decompositions. These are going to be things that just don't make sense to me for a while. I can tell this is like the end of the course when I start applying linear algebra to things. This is a good, I think every math teacher should, at some point in a math class, ask this sort of question, whether it's algebra, calculus, whatever you're learning. This is kind of neat. I'm seeing like, okay, this isn't unimportant. This is a fundamental language of the universe right here, which math should ideally be taught as a fundamental language of the universe. So in biology and chemistry, we have genetic data is a matrix of expression levels of expression of genes. Molecular orbitals are solved by eigenvectors and Hamiltonian matrices. Digital signals in music are vectors. Filters and transformations are matrices. A Fourier transform, matrix. That's why compression, pitch shifting, reverb. This is insane. Okay. These all are like a full hour probably plus of understanding, but I'd like to get into this. I'm just going to screenshot all these. In computing, graphics, transforms, animations, camera movement, matrices. That they've actually talked about, and I kind of get that. With the whole transformations and animations are matrices. Compilers, dependency resolution, matrix. Optimization, cost functions, constraints, and updates, matrix. Why do matrices feel arbitrary? Because they hide complexity beneath their simple form. They look like rectangles and numbers, but they represent mappings between spaces, rules of interaction, symmetries, constraints, and dynamic systems. They are the DNA structure in math. Once you get used to them, you realize they aren't arbitrary. They're the perfect compression of abstract linear behavior. Dang! A matrix tells a story about how inputs become output, how motion, data, or forces travel through structure. That's why mathematicians, physicists, and engineers all speak matrix fluently. This is one of the most interesting. This is maybe the single most interesting response to a prompt I've gotten. And just to go back up to the prompt, if you want to see it, why matrices? Why are these a fundamental way of containing information? They seem kind of arbitrary to me, so help me understand what their rows and columns mean and why they mean that and why they are important to the mathematics as the universe as a whole. So just kind of the whys. A lot of whys makes GPT go off. 1, 2, 3, 4 whys in this short prompt. I want to ask it the same about functions and algebra because I see a lot of these things overlapping with what my understanding of an algebraic function is. But let's go back to this lesson plan here. Practice problem 1 completed. Find the kernel and image of t. Okay. To find the kernel, I just realized they're all scalar multiples. So the kernel of t, I have to do row reduction. Okay, I should actually write this out. And sorry this lesson's abbreviated. This is actually a really meaty lesson that I'm just kind of shortchanging by only trying to do it in half an hour. Just got to run my daughter to the dentist. So life happens, but this is the foundation of life, I guess. Matrices are everything, is what they just told me. So a kernel is the null space of A. I get that. So to find the null space of A, I row reduce this. And it becomes 1, 2, 0. Oh, excuse me. Yeah, so I think the matrix would become 1, 2, 0, 0, 0, 0. Which means I'm going to have x1 plus x2. So therefore, plus 2x2, because it's a 2 on top. So x1 equals negative 2x2. I want x2 to equal t. So therefore, it's going to be t times inverse of x1. I get -2 and then 1. I didn't turn this on Do Not Disturb. So it's this line through the origin in R2. So I need to get used to these sort of functions. Span of this. I want to understand better what that means. Cur, span, all those things should really gel for me by the end of this. An image is the column space of A. So the column space is just the span of one vector. So 1D subspace of three-dimensional space. I just take that 1, 2, 3. Is it 1, 2, 1? No, because the kernel is not trivial. That's something I need to make sure I understand. Is it onto? No, because the image is a line in R3. Okay. Whew. Practice problem 2. Every linear transformation maps the 0 vector to the 0 vector. True. If you have c equals 0, yeah. If t is 1 to 1, then the kernel of t equals the 0 vector. That's the definition of being 1 to 1. No two different inputs map to the same output. I'm going to want to definitely screenshot this one. No two inputs map to the same output. Only solution to this equals 0 is x equals 0. The x vector has to be 0 for it to collapse. What does 1 to 1 mean in algebra again? That means it passes the horizontal line test, meaning that the inverse is also a function. Oy, oy, oy. Okay, and then if A is an element of a 3 by 2 set of real numbers, then t of the x vector equals A times the x vector into R3. A summary, okay, so this is false. A transformation from the second dimension to the third dimension cannot be onto because the image of A is at most two-dimensional, but it has this. So there's no way it can fill the whole three-dimensional space. Okay, we're sort of getting this. Give me a quick concept practice quiz. This lesson's gnarly. I'll just say it right now. This lesson is intense. So I definitely want a quiz here. I'm going to ask it to just explain what all these symbols means. Holding that. Explain. So the domain of T is going to be I want full solutions to the above. For matrix transformation not to not be not one-to-one means that geometrically there is some transformation that can make it go on the 0 vector. I'm not sure if that's fully right. Maximum possible dimension of the image of A, the kernel of A. I think that for the image of A, it's 3. For the kernel of A, is it 2 or is it 5? I don't know. True or false? If this is a linear transformation and the rank, then T is 1 to 1. The rank of A is equal to the number of columns of A. I'm guessing false. Not sure though. T is the name of a transformation. Oh, T is transformation. I should just write that. T equals transformation. guess that sort of makes sense. The domain of T is in 4 dimensions. The codomain is 3 dimensions. Oh, input, output. Okay. So we're transforming this from a 4-dimensional space to a 3-dimensional space. This defines the action of T for any input vector. Apply the matrix to it by multiplying. A is a 3x4 matrix. It has 3 rows, 4 columns. From A maps from 4D inputs to 3D outputs. Cool. Multiplying A by a 4x1 vector results in a 3x1 vector. Intuitive meaning. Oh boy. All right, so this transformation is linear, meaning it respects vector addition and scalar multiplication. It can be described completely by its effect on the basis vectors. Dang. All right, I'm going to get full solutions to the above problems, then wrap up this stream because I do have to run. But man, this is getting fascinating. This is exhilarating right now. So the domain is 4-dimensional space. Let me look at these and see if I can answer it now. Domain, R4, real numbers in 4-dimensional space. Codomain, real numbers in 3-dimensional space. Image, I think 3-dimensional space. Kernel, let's see what they say, is in 4-dimensional space. The dimension is equal to the rank of A. The dimension is equal to the nullity of A. Cool. True or false? It is 1-to-1. Okay, so if the rank of A is the number of columns, then there are no free variables. The null space is 0, so there's no kernel. Or the kernel is the 0 vector, meaning that it's 1-to-1. Okay. It's so annoying when they don't get the math formatting right. I didn't even look at the Claude. I'll look at that later another time. Max dimension of this image. The image is the column space of A. So it's the most is 3. Max dimension of the kernel is 5. It's the rank plus nullity is 5. I have 5 columns. Nullity is 5 minus the rank. I could have 0 rank here. Interesting. What does it mean geometrically for a transformation to be not 1-to-1? There exist input vectors such that a transformation of one input vector is equal to a transformation of a different input vector. Okay, so that's similar to what it means in algebra. Equivalently, I could take these and subtract them to get the 0 vector. Some directions in the domain get collapsed to the 0 vector. The kernel is non-trivial. Vectors along the kernel all get sent to the same point, 0. So the transformation loses information. All right. Wow, that was a really intense 30-minute lesson, but thank you for tuning in. I'm running out right now. I'll record a short with some recap from today, but there's a lot more for me to do, and I'm actually going to start posting some other stuff as well. So follow along. Thank you for tuning in, and let me know your thoughts about learning with AI and using this tool to learn something really foreign and intense like linear algebra. It's been a journey so far. So stay tuned. I'll catch you guys later.